record this, even though we're all here. What we do have coming up, not that anybody's forgot, is next Tuesday we have our second exam, right here at the end of the semester. It won't probably be in 333, probably in this room, whatever this is. What room is this?
223? I don't know. I guess I would say 222. On the pattern, but I don't think so.
Right. And then on Friday, we have presentations, right? And that probably won't take too long. So we're left with today and Wednesday. And so maybe what we'll do is we'll just, use one of these websites. We'll just do some practice, solve some problems. And I was on my computer up there this morning, and there's this website. I don't know if we used, maybe we did that one, called NMR Challenge.
Yes, yeah.
But I went down to the ones that have the 2D stuff, because before I did the challenging ones that have 1D, and they were all pretty easy. And I did this one, just randomly pick these ones with 2D, and I just totally got stuck. And I was up there, and I'm like, oh, shit, I can't. I almost didn't make it down to class because I couldn't leave without solving this problem.
Well, it's good practice then.
Well, because it had probably in the carbon, probably a carbonyl or something at 177, but there was one at 156, kind of upfield for carbonyl, but no aromatics, no double bonds. There was only a methyl group. It was at 50 in the carbon and 3.0 in the proton. And then there were 3 CH2s that 2 of them might be equivalent and another one just barely different from it. And they're all singlets in the proton NMR.
Oh, God.
And, yeah. Maybe if I pick them randomly on Wednesday, hopefully that one won't come up. Or I'll go up there and spend the rest of the day trying to figure that thing out. Because you can draw in the structure, but you can't just say, click, show me the answer.
Yeah, you actually have to give them the answer.
Right.
Yeah.
And I guess I always got them all correct before. So I don't know if you get 3 strikes and you're out and they finally show you the answer, or if you just never get to see it if you never get it right. All right, well, okay. So those are the things we got coming up. Last time we talked about started talking about stereochemistry. We talked about the difference between relative stereochemistry and absolute stereochemistry. So relative, like it implies, is just the relationship of one chiral center, for example, to another, right? Cis or trans or whatever like that. Absolute is the actual R or S of each of those chiral centers. So that's like telling the difference between one enantiomer and another. So last time we went through some methods to determine relative stereochemistry. So one of the main methods was just looking at proton-proton coupling constants. And we looked at one method to essentially take 1,3 diols and make them into a 6-membered ring so it would have discrete conformation. And we made these acetonides, and in that case we actually just looked at the C13 of the methyl groups of the acetonide. We looked at using NOE, and in ring systems, like cyclohexanes, remember that one good place you can see NOEs that give us some stereochemical information is between like 1,3 diaxial arrangements. So if you have some, some group here and some group over here that tells you whether those groups are equatorial, I guess. And then we kind of went through just a little bit to demonstrate that there is a way, not that we really worked through the whole thing, to use proton C13 coupling constants. So J2 and J3 proton carbon coupling constants for acyclic systems. All right, so today what we're going to do is just go over some methods where, that reminds me, where you can determine absolute stereochemistry. And I forgot, well, we'll get to that here. There was something I probably should have looked up that seems to be common now, but I don't know how to do it. Using CD, so we're going to go over circular dichroism a little bit, but I think that there is a way to take a compound and calculate what the CD would look like. And you can match that to the experimental data.
That's nice.
But yeah, I've never done that before. All right, so first off, when we're talking about chiral molecules, we oftentimes talk about optical activity. And this refers to the ability of chiral molecules to rotate the plane of plane polarized light. And we'll look at a cartoon of this. Chiral molecules tend to and another way to think about it is that they tend to absorb right and left circularly polarized light differently. So if we talk about using plane polarized light, this is kind of a diagram. So here's our light source over here. And we can think about this light source as having, light as being a wave. So here's our wave. But this is in a plane in this direction, and those planes are oriented in all different directions. Okay? So we send that light through this polarizer, which you can just think of as like a grating here or screen, and only light that's oriented in one direction can pass through. Right? So it comes out, we have then just light of a single plane. That light passes through our sample, and if the molecules in that sample are chiral, then they tend to rotate this plane of polarized light one direction or the other. Okay? In this case, they're saying that this is rotating it, to this direction. Well, that shows 90 degrees or minus 270. And so then they essentially have this other grating that gets rotated so the light will pass through, okay, with the detector over here. So if we're running this sample, we get some value of alpha. How many degrees the light is rotated. But that amount of rotation is dependent upon things like the path length or the cell length, so how much length the light has time to interact with the molecules, and the concentration. Okay, so we usually report for chirality what's called the specific rotation. So this is essentially normalized for the concentration and the path length. It's kind of like the...
1 unit for all of them?
Huh?
Is it kind of 1 unit for all of them? For example, 1 centimeter, 1 mole per...
Well, usually in this, I think, use... it's like 1 decimeter or 10 centimeters. But I think the unit for the equation is decimeters, right? We always use a unit, so essentially the path length equals 1, right? So in Beer's law, right, for UV vis absorption, we use 1 centimeter because we usually use a 1 centimeter cell length, right? But if you did use a different cell length, then you would have to take that into account. Concentration is usually in grams per milliliter. And the light that is most commonly used just for normal specific rotations is the sodium D line, which is at 589 nanometers. So we're not really looking at absorption, like UV visible absorption, but we're just looking at rotation of the plane polarized light.
So what does sodium D line do exactly? Isn't it?
Standardized.
Oh,
Wait.
is it plane or?
Yeah, it's just a standardized wavelength. Right. So you could use different wavelengths, but if we use a standardized one, then it's easier for one group of researchers to compare their results with somebody else's result. Yeah.
How'd you be able to tell that it's like 90 degrees and not 270?
Yeah, that's a good question. I think what you might have to do in those cases is you might have to vary the concentration, right? Because if it was right at 90, if you made it a little bit less dilute, then it should go back a little bit, right? So you should be able to see a movement in one direction, clockwise or counterclockwise or something like that.
How do you get, because there's been reported of like greater than 360.
Oh, right.
I don't know how you would get that. Well, no, I guess you would do the same thing. You'd vary the concentration, and if you start, you lower it, and if it still keeps going after you continuously lower it, then I guess it's however many rotations it does through your sample cell.
Right, that any concentration you could just keep going like up to like.
Well, no, because there would be only so much that it could, like you start here or you start at 0, and then at a small concentration you might only move it like a little bit, but if you have it very concentrated or the optical activity is like very strong, it may just like very quickly go through 360 and then go again. But if you have like almost nothing in there and you decrease the concentration, it's still going to be about 0. But if it's hypothetically 360, you'll go to like 280.
Right, and I think the thing would be too is that what you're doing is you're actually calculating. This is the standard value that we report, is this alpha D value. And so this is the experimental alpha divided by the path length 1 and the concentration, right? So if it rotated around for over 360, or it looked like a small rotation, and then you made it more dilute and it went less than 360, and you divided by the concentration, then your alpha D should come out the same no matter what the concentration, right? But if you said it was like plus 10, but it was really 370, and then you did it less and it was like 180, your alpha Ds wouldn't come out the same if you used 10 and something less.
Yeah. That's, oh my gosh. Makes sense. Because
Yeah, you're not just looking at the measured rotation. You're dividing it by the concentration. So that should, in theory, come out the same. Though I think you usually wouldn't. Well, I don't think you'd usually use a really high concentration. So I don't know how many times that rotation would go, around more than once.
I do have.
Yeah. Okay. So this is usually what you report, is this alpha D, and then oftentimes what you also report is the temperature, because its temperature can be temperature dependent as well, and and the concentration at which you ran the sample, and probably what solvent you did it in as well. All right, so there are some other experiments that you can use. One is called optical rotatory dispersion, or ORD. And what this is essentially a plot of the alpha D versus the wavelength. So this is recording the wave, doing it at the rotation at different wavelengths and see how that changes the rotation. So here's two examples, these two compounds here, 16 and 17, and essentially what they're showing is a curved plot for these different rotations. Here's the wavelength down at the bottom, wavelength, versus the specific rotation, right? And so for these two compounds, notice they have different curves, but they're not enantiomers, they're actually diastereomers, so you'd expect them to have different curves. Okay, so more commonly, though, I think people will use circular dichroism. So we can also think about polarized light as being circularly polarized. And we can think about, instead of just this plane, we can think about that the light is made up of two helical components of light, right? One is going around in one direction, and the other one is going around in the other direction. And if we looks kind of like NMR that we've been doing here. If this one is going this way and this is going this way, if we sum them together, we just look in one plane here, we have a component here. If they go, each side goes out further, we still have this component in this direction, but it's getting smaller. At this point, the direction in this plane would be 0. Here it would be starting to get negative. Here it would be stronger negative, right? So if we look at just the component of it in this plane right here, as they're adding together, as they're going around like this, then we see just an oscillation like what we were talking about before. And so in circular dichroism, what it's really looking at is the absorption, the amount of absorption in one direction versus the other direction. So the difference between the essentially the molar absorptivities of the right polarized versus the left polarized light. So in this case, what we have is our light source. This is unpolarized before going through there. We have our polarizer. So then we have a linear polarized light. So this is equal component in both directions. Goes through, I'm not quite sure what this is. So this is the, I hate that thing down there. The photoelastic modulator, which I'm not sure what that is doing, but it shows it splitting out the two components of the circularly polarized light. Goes through our chiral material, and we can see here that the right circularly polarized light is stronger than the left circularly polarized light, and it measures the detection, measures the difference between those two. CD is common for identifying different components of like DNA and protein. Usually there are these like tertiary structures, like different types of helices and beta turns and things like that. So they give characteristic CD spectra for these different components of those larger structures, but it can also be used to determine the chirality of small molecules. So one way to use it is we'll show one example of that, is to compare it to essentially a known compound and match it. But what we'd like to really be able to do is, calculate it out or determine the chirality of a structure without having a known, really. Okay, so the difference between the optical rotatory dispersion versus the CD in their spectra is the CD gives either a positive CD or a negative CD, and the maximum of that corresponds to where the ORD goes from negative to positive. And this point at where the ORD goes from negative to positive is referred to as the Cotton effect. Okay, and so we see it going, from plus to minus, and it goes through 0. There are some, also, these are kind of older, but what are called sector rules for CD, for these Cotton effects. And this one that I'm showing here is called the octet rule, because they break this coordinate system into 8 different...
They're really running out of names.
Huh?
So they're really running out of names.
So in this case, this works for ketones. And so what they're doing is they are lining the ketone here into the kind of the origin of this axis system. And so then the molecule, let me see how I drew this before. If we look at it from in the front, our ketone goes this way, and then the ring system essentially goes up like this. So if we're looking along this axis right here, and what it does is we have plus and minus contributions all around this coordinate system. There's my drawings. So, for example, if we're looking here, we're looking back where the main part of the structure is. We have a plus down here, a minus up here, a plus over here, and it should be a minus down over on the other side. So if we looked at these, we would have a plus and a minus and a plus and a minus. Okay, so if we have a structural component over on this side over here, that's going to add to the plus. So here's this CH3 here. So from this, we would expect to have a plus Cotton effect. Or in the CD, it would have a positive value. Okay, for this other one, the enantiomer puts the methyl group over in this other quadrant, which would be a negative quadrant here, so we would expect a negative cotton effect over here. Right, so the CD spectra should be exactly opposite for enantiomers. I think there's some other rules, not only for ketones, but there's some other rules that people could use like this. The way that I've used CD, well, is both the matched is essentially standard, but also used this method, and I don't know the physics behind this, but it's called the exciton chirality method. And what it does is it predicts the helical orientation of two different chromophores. Okay, so for example, here's this molecule here, and they're looking at these two different chromophores which are oriented around the helix like this. And so if you look down this axis, down the axis, then here's the drawing. There's one chromophore going this direction, right here, and the other chromophore behind it is going perpendicularly. And so you look at the rotation from the one in front to the one in the back. Okay, so here they're saying, oh, this is a positive rotation. And if that is the orientation, what you should observe, this is the actual CD up here, and you get this split CD with two different cotton effects. And if the way that I think about it is if you come in from the higher wavelength, if you have a positive rotation, you have a first positive peak here. So if it goes positive to negative, then positive means you're going to have a positive rotation. Here down here, I guess these are two, I didn't even read this all down here. I think these are the two separate, let's see here. What do they say? A has the split cotton effect, application X, still I guess these are the two individual CD parts, but here in the bigger one is the lambda max for the compound. So notice that the split cotton effect goes through 0 at the lambda max of the chromophores.
Why that we have, if you have several different chromophores in a chemical structure, each of them have their own rotations, and their summation may have different rotations in general?
No, I think that not each chromophore will have a rotation because it has to do with the chirality. So it's the orientation.
If each of them has a chiral center.
Right.
So each of them will have different rotations because of the chiral center.
Well, I think it's more the sum of all. It's I don't think you can necessarily split them all out in this. And the way this, you're going to have an overall rotation or an overall CD spectrum, which may have components between the relationships between these different groups. And in this case, they just have a molecule that has these two chromophores. And the chirality, we haven't, here isn't because of a chiral center. It's because of the orientation of these, right? So if we rotated this group, around, so the OH and the O-methyl would pointing the other direction. So this only really works if it's kind of either stuck in this direction or this direction. It can't rotate relative to the other. And so then you could either have this positive rotation or negative rotation. And if if the OH and the methyl here were flipped 180 degrees pointing the other direction, then you should, then you would have, this one, and the other one would be pointing out this, and you'd have this negative rotation. Right, so you'd see just the inverse or the mirror image of that split CD spectrum. Yeah, I don't know exactly how all this works, but we've done this and know kind of how to interpret it. Get back. Oops. So the example that we use, so we talked about this compound here before, right? And we went through how we could use coupling constants and NOE to determine the relative stereochemistries of this group and of this group over here. Okay, so what we talked about was that the challenge then is how to determine essentially the absolute stereochemistry of one group at least, and then how the other group relates to that. Or what we actually had to do is determine the absolute configuration stereochemistry of each end independently. And that would then give us the relative between the two ends. So the left end, down here, all we did is we ran a CD spectrum of this molecule and said that, this chirality on this end is directly attached to the chromophore. And what we did is we compared the CD spectrum of that compound with the CD spectrum of this smaller system as a standard, essentially. So this compound, it was known in the literature called naneomycin. So here's the naneomycin is this one. This is in green. And the compound that we had is this one in red. And we said essentially that these are almost mirror images of one another. And so that indicates that this end of the molecule has to be opposite to what this naneomycin did. So notice down here we have this methyl group going back and these two ones of the ring going forward. So we have this ethyl now coming forward and these going back. So we assign this as being opposite of this known compound. All right, so we didn't do it kind of from scratch, but we compared it to a known compound. To that other one. Oh yeah, we'll do this other half in a little bit. I think. Okay, so another compound that we had that we wanted to determine the absolute stereochemistry had this sugar on the end here. Okay. And we were able to determine the relative stereochemistry of that sugar just by looking at proton-proton coupling constants. Because we could say from this anomeric position here to this was a small coupling constant because it's equatorial to axial, gauche. But then going from here to this one, and from that one to the next one, and from here over to here, these were all large coupling constants. Okay, so we could fix all of those diaxial coupling constants, and so all of the two OHs had to be equatorial because they had axial protons. Okay? So then, in order to apply this exciton chirality rule, the way people do this for these diols is you derivatize your compound with as benzoates, right? So you add these two, even though we had a chromophore, we add these two chromophores out here. And then we run the CD spectrum. And in this case, if we look at the molecule down this axis right here, then what we see is with the front, I'll redraw, there's a tiny picture there. The front benzoate would go up this way, and the back one would be down like this, goes to each other. And so we go from the front one to the back one, and so this should be positive. And I think as we came in this direction, this is really the first one here is positive. So that's how we assign the stereochemistry. I guess the drawing that I did over here is not drawn in the same orientation of the sugar. But that's how we assign the absolute stereochemistry of this group. I don't know if you could actually do it. I think maybe the two chromophores have to be relatively similar, maybe in lambda max.
What will happen if they don't have any similar lambda?
I don't know.
They will mix, or
I don't know, or
they may have two lambda max.
yeah, I'm not sure. Because, you know, this has this bigger chromophore here, but that would absorb at a longer wavelength.
Because it happens that the chemical has two lambda max. One of them is smaller and the other one is bigger. Because of different chromophores that it has in the same structure.
Well, if you have just different lambda maxes, then you can just have different absorptions. But I think maybe because this point here is supposed to match, and I didn't look this up, but this should match to the lambda max of this, you know, benzoate. But, you know, this other one, this kind of would be much longer wavelength. I do know that people do use some other chromophores. The benzoate was the common one when this method was first reported, but you know, I've seen also with using it with like, you know, naphthalene kind of chromophores like this. You know, this would be derivatized here. And I think it makes it stronger, but it would also shift it to a longer wavelength. And maybe away from other absorptions or something. Okay. All right, so the last method that we're going to actually go through, and there's a bunch of variations of this as well, and more in-depth, you know, treatments as well. And this was referred to as the modified Mosher's method. So this is kind of referred to as Mosher's acid. So it's this. Well, this isn't the acid. This is the acid chloride to do the derivatization. If this was an acid, then it would be Mosher's acid. And so it has this chiral center here with a trifluoromethyl methoxy in the phenyl group. And you can buy either the R or the S. And you can buy of the acid chloride. So typically what this is used for is to derivatize an alcohol. Or I think they've actually used this for amines to make amides as well instead of esters. The original Mosher's method, what they did is I think that they looked at the fluorine NMR of the trimethyl group, trimethyl fluoro group. trifluoromethyl group.
That would be interesting.
Trimethylfluoro
That would
group.
be interesting.
So the way that this essentially works is if you have a single chiral molecule that has, for example, a secondary alcohol here, then you do two different derivatizations. You derivatize this with the R acid chloride, so you make the R ester. This is, I guess, methoxy trimethyl phenyl acetic acid, MTPA. And you do it with the S, and so you make the S MTPA ester. You record the proton NMR spectra of these two derivatives, and typically the way that this has been done is you calculate the difference in chemical shift from the chemical shifts for the MTPA ester. You subtract from that the chemical shifts for the R compound. So, for individual protons around the molecule. And the way the analysis goes is that it was said that this is the preferred conformation of the ester, with the trifluoromethyl group in the plane of the carbonyl, putting the phenyl group on one side and the methoxy group on the other, right? And for the other enantiomer, those two would be switched. And so the idea is that this phenyl, I guess we never really talked about this so much. Remember that for a benzene, around the edge, around the edges, we usually see de-shielding, right? Downfield, de-shield. But if something is in the middle, then we see shielding. So if we have a proton that we push towards the face of a benzene ring, it can cause it to be shielded. And so usually the groups on the side of the phenyl group, so if that's sticking out, it would be these groups over here would be more shielded than the groups on the other side, right? And if we did the other enantiomer, then the groups on the side of this phenyl group, in this case, would be shielded over here. Okay, so the chemical shifts, this delta should work in a predictable fashion. Okay, so for example, let's see if we can figure this out. If we're doing the S minus the R, so S is in red, these would be more upfield here. And the other ones, I guess, would be, so it would be upfield minus downfield, and these other ones would be opposite. So upfield would be a smaller chemical shift minus a bigger one, so it would be a negative value, right? So on the left side, this is a negative value. The delta is less than 0. And on the other side, it would be just opposite, so this side should be positive. So you run the two spectra, you identify the peaks, you subtract the chemical shifts, and what you really should see is on one side of the molecule, these deltas should be negative, and the other side, they should be positive. They had the OMTPA up. So here's some examples from that paper. Okay, and it's kind of an old paper at this point. So here's where the derivative would be the MTPA esters. And so, and the plane here would then go right up through here. And so what we're looking for is negative delta deltas, and we usually do these in hertz rather than parts per million. You could do it either way, but it makes bigger values in hertz. So we notice these are negative, 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 negative on this side, positive, 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 positive on the other side.
Is it through bond shielding or because of their spatial orientation?
The spatial orientation, yeah. Because the phenyl group is going to be, it's going to be kind of a ways away, right? Because it has to go through the ester to the chiral center. In these other ones, let's see, here's the ester here, so that plane would go up through here somewhere. And so we see negative, 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 negative on this side, positive, 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 positive on this side. And it kind of works the same on all of these. So if you did this experiment and you didn't see a pattern like this, what do you think that would suggest?
It's an achiral.
Well, I think if it was achiral, then you just... Well, the chemical should be exactly the same on both. Well, you'd have two... Well, you wouldn't have two enantiomers.
That's true. Well,
Well, you're making actually diastereomers here. So this is the key, right? Is if you had the two enantiomers of the natural products, which you probably would only have one, the chemical shifts would be identical for either enantiomer, so you can't tell based upon that. So what you do is you derivatize it with a chiral derivatizing agent, and you make essentially a pair of diastereomers. And diastereomers have different properties, and so the chemical shifts are different. So I guess what I was thinking is if you had pluses and minuses on both sides, what it suggests is the molecule isn't adopting this kind of preferred conformation with this plane down the middle. So because of sterics or something, maybe it's like it's in some different orientation. They draw that. Okay, so here's our molecule. So remember, we determined the absolute stereochemistry of this end just with the CD spectrum. And so we did this derivatization here. We have the OMTPA, and so essentially our plane goes through here. And so we have, and let's see, which way? And so we have, let's see here, I can't picture that. These are, God, that almost, is this the one I did before? CD. It almost looks to me that these are, the way we have them drawn here are opposite or something. But we see positive over here, negative, negative, negative on the other side. So we do see this split, of positives and negatives. So there's also other treatments that of these that say, okay, it doesn't really adopt this one conformation, but there's several conformations, and then they treat those. And in this paper, if you ever wanted to do any of this kind of stuff, this review article, well, it's still pretty old now, talks about all kinds of different ways to do these with different derivatizing agents. And there's some of them that you can do, and I think we did this one time, where you don't actually have to do derivatize twice, but you derivatize it once, and then you vary the temperature. and then you see some predictable difference because the equilibration of the different conformations changes at the different temperatures. And you can do it not only at the secondary position, but there's some where there's a chiral center here, and it's like at the beta position, the next one over. And I think amines, and they have different equilibrations as well. But it seems like now what's done, and I don't know if you guys might not have been here for the Olson seminar a number of years ago. We had Bill Fennicle from Scripps Institution of Oceanography come here. So he's a well-known marine natural products guy, and what they could do is they can do essentially a CD spectrum, and then there's a way to calculate what the CD spectrum should look like for the two different enantiomers. So you don't actually have to do anything else beyond that. But I'm not sure how general those, I tried to look this up a little bit one time. I'm not sure how general those calculations are, if there's, common, programs or packages that you can use to do those, or if you need some expert at that stuff, if it's easy to do now for your basic organic chemist, or if it's more than that.
Cool. That would be helpful.
Yeah, right. All right, so that's basically all I've got for you.